The team made a craniofacial synthetic bone graft, and the team members were Kristen, Seth, Nolan, Kylie, and Parker. The clients were Dr. Puccinelli and Dr. Nimokar. The team had to design a synthetic bone graft to fill a bone defect that was 20 millimeters deep by 60 millimeters in diameter. The graft had to maintain mechanical stability similar to native bone under physiological conditions for at least 2 weeks. The team chose the craniofacial region because patients with tumor resections, facial trauma, and congenital disorders all can require the surgical replacement of bone in the craniofacial region. Over a 4-year span at the Seattle Children's Hospital, 12,371 patients were treated for craniofacial conditions. Some craniofacial conditions include cleft lip or palate, craniosynostosis, and jaw and ear abnormalities. Craniosynostosis commonly leads to craniofacial implants, and it is a congenital deformality of the infant skull that occurs when the fibrous joints between the bones of the skull close prematurely. The baby then develops an abnormally shaped skull. Autografts are the current gold standard when it comes to craniofacial grafts, but this requires multiple surgeries and there can be high morbidity at the donor site. Common autografts for craniofacial defects come from the iliac crest bone and calvarial bone. Synthetic materials are gaining more traction with increasing technology, and some common materials include calcium phosphate, calcium sulfonate, and PMMA for craniofacial grafts. The team had design criteria for 3 key elements of the project: the sample holder, the electronics part, and the synthetic bone graft. The sample holder had to hold at least 6 samples and be easy to remove the samples. It also had to be safely used by the operator. The electronics had to heat the solution to 36 and 37 degrees Celsius, and the circuit had to read and display sample holder temperature and alert the team when the temperature was out of range. The synthetic bone graft had to have similar mechanical strength to craniofacial bone, and the graft had to maintain the strength for 2 weeks and had to be biologically compatible. And now Kristen will talk about the biomaterial.
For biomaterials, we considered 3 different options. We talked about calcium sulfate, calcium phosphate, and polymethyl methacrylate. Ultimately, we chose to go with PMMA because it's inexpensive, easy to fabricate, highly biocompatible, has minimal bone resorption, and is highly moldable, which is important for craniofacial applications since it's so individualistic. Some of the disadvantages we found when we were researching were that it's an exothermic reaction, so it must be polymerized outside of the body, and sometimes when surgeons are injecting it into the patient, it can cause burns around the injection site. It also has high mechanical properties, which can cause stress shielding, which we'll talk more about later, but that can cause bone resorption of the native bone. It's also biologically inactive, meaning that it could potentially loosen from the native bone and require additional surgery. For the fabrication of PMMA, it's a pretty simple process like we talked about before. It polymerizes through a free radical mechanism, and it involves mixing a liquid component with a powder component. It includes an initiator of benzoyl peroxide, which initiates the polymerization reaction. The team didn't run any biocompatibility tests ourselves, but we were able to find several sources online that did ISO tests on it. They were able to determine that it is not cytotoxic. We also found tests that were done with enzymatic markers. They determined if in vitro the PMMA was supposed to cause a immune response or cause the degradation of the membrane, which would indicate that it's cytotoxic, and neither one of these enzymatic markers increased when PMMA was introduced into the system. The degradation of PMMA in the body is a very slow reaction, and it's considered to be non-biodegradable, but over time it does undergo hydrolysis because it has that ester group, as you can see in the monomer structure we have on the right. But again, this is something that we don't expect to be an issue in the span of the implant's life. And now we're going to go to Kylie to talk about the electronics that we designed and how we tested that circuit.
So the thermistor and was sitting in solution with the bone graft, and the thermistor was there to measure the temperature of the bone graft solution. The thermistor was sitting in the circuit on the right in a voltage divider connected to a non-inverting amplifier. As the temperature of the thermistor changed, the value of the resistance changed, which changed the output reading into the Arduino microcontroller for the output voltage. We then changed this ADC value to display an accurate temperature reading for the values, and it was accurate between 28 and 40 degrees Celsius, which was good because our solution was staying between 35 and 38 degrees Celsius anyways. If the thermistor measured a temperature that was out of range, the team would receive an alert when the temperature got below 35 degrees and above 40 degrees Celsius. Now Seth will talk about the sample holder holding everything in the solution.
Thanks, Callie. The sample holder is critical to the project because it ensures the biomaterial samples will be successfully exposed to the solution in the bioreactor. The final sample holder we designed allows the biomaterials to stay organized and can grow and swell if necessary. The design we created is one with 2 rectangular prisms, each containing 3 samples. After 1 week, one of the prisms would be removed so testing could ensue on 3 of the samples. After the second week, the remaining samples would be removed and would be tested for their mechanical properties. Without access to the team lab, the team determined that utilizing the Makerspace's laser cutter would be the best way to fabricate the sample holder. The team also determined that using 1/8 inch acrylic would be the best material to make the sample holder from, as it would only be marginally affected by the buffer solution in the bioreactor. To fabricate, the team sliced the design first created in SOLIDWORKS into individual pieces in Illustrator so that the pieces could be uploaded to the Universal Laser System software and be vector cut by the laser cutter. After being cut, the pieces would be fastened together into the prisms with acrylic glue. After the glue set, the sample holder would be ready for use in the bioreactor. Both one of the prisms in SOLIDWORKS and the Illustrator part designs can be seen to the right. Up next, Parker will be talking about the testing and results.
For the mechanical testing and results section of this project, the team decided to use an MTA machine to test the PMMA samples. The testing protocol laid out by the team involved sample acquisition, which generally involved making sure that the samples were ready to be placed in the MTA machine for accurate results. 2, preparation of the MTS machine, which mostly involved attaching 10 kilonewton compressing plate and fixtures to the load cell. 3, running and collecting the data, making sure that we are collecting data safely and accurately as the tests were being run. And 4, statistical tests, which I will go into on the next slide. The outcome from the mechanical testing was the elongation, load, and time values for the data sample. The statistical analysis and results, mainly I ran the t-test of the max stress values for each time period in order to compare and see if the time values that were being compared were statistically significant or not in terms of how the values changed over time. As you can see on the slide, comparing time 0 to time 1, the p-value is 0.9605, which in general terms of mechanical engineering industries, that is not statistically significant change in values. And then for time 1 versus time 2, the p-value is recorded as 2.1680, 10 to the negative 4th, which is in fact statistically significant. The elastic modulus test mostly showed were found by using the max stress values over the max strain values for each time period. And those samples were then shown as samples 1 through 9, the range being about 90 to 278. And comparing that to cortical bone, there is a large gap in the comparison. However, because the team is focusing on a facial reconstruction, we were less concerned with shearing stress. However, that being said, of course, for future work, it would be important and something that the team should look at in order to try to minimize that gap. Now Kristen will talk about future works.
So thanks, Parker. So when we were finishing this project, we were looking at some of the future work that should be done in order to improve the synthetic bone graft. Like Parker just mentioned, the mechanical properties of PMMA is greater than that of cortical bone. So future work should be done to increase the pore sizes within the cement or add other chemicals in order to decrease the mechanical properties to reduce the risk of stress shielding. Even though, like she said, we're not as concerned since the craniofacial region of the body doesn't undergo repeated loads. Craniofacial applications are also highly custom. As you can see on the right, there's a very specific shape that the bone must fill. So mechanical testing should be done of these various shapes and sizes to understand how the mechanical properties of the sample will be affected based on the different shapes, in order to make sure that stress shielding is still not a factor when implanting these craniofacial implants. So that concludes our presentation. We want to thank Nathan, our TA, as well as Dr. Cuccinelli and Dr. Niman-Carr, and all of our essays for helping us along the way.